All right, pages 5 and 6 of the quiz review right here. Number 12 says, verify that this satisfies the differential equation. So anytime we're trying to satisfy a differential equation, make sure you know what you're working with. Our y, our function, is x squared plus 2x plus 2 plus c e to the x. Anytime we see y, that's what we're plugging in. Y prime then will be 2x plus 2 plus c e to the x. Anytime we see y prime, that's what we put in. If we had to do y double prime, we keep going, it doesn't matter, right? So here's what we have. We got y prime. So I'm putting in 2x plus 2 plus c e to the x minus y, x squared plus 2x plus 2 plus c e to the x, okay, plus x squared equals 0. So now if I distribute this, I get 2x plus 2 plus c e to the x minus x squared minus 2x minus 2 minus c to the x plus x squared. Well, now you can see everything cancel. X squared's 2x's, 2's, c to the x, everything's gone. We get 0 equals 0. There's our verification. All right. 13 wants us to write a differential equation. It says the rate of growth for a population of deer. So this is going to be change in population over change in time. We'll get that set up. Is proportionate. That means we'll have some constant of proportionality, something that keeps these in balance. All right, and is proportionate to the population of deer. So we're going to multiply by the population of deer, and also to the difference between 4,000 and the population. So also multiply by the difference between 4,000 and the population. So it's called the logistic differential equation. We'll get into this more in just a second, but that's how we would write it. 14 gives us a slope field, wants to know which of the following could be a solution here. So if you kind of trace out a possible solution, just to kind of get an idea of what we're dealing with, all right, this is kind of what I see here. And cosine kind of goes up and down. That's not what we're seeing here. I would get rid of that. This 1 over 3x kind of looks like this if you graph it. Not what we're looking at. X cubed over 3. Kind of looks like that. That's got some promise to it. X squared we know looks like this. Natural log function kind of looks like that. So of our choices, for sure, C looks the best, right? And you always want to kind of go with your gut on that one. And if it says which of the following is the differential equation that created, that's a different story. Now we have to look for when is this 0 and which one of these matches up with something like that. But if it's just saying which of these could be a solution, then that's how we go. All right, 15 wants us to take this with an initial condition 2, 2, and can we get an approximation for 1.4 in 3 steps? So it's always a good idea to set up a table to kind of guide us here. So we'll have x, we'll have y, we'll have dy dx, or y prime if you'd rather, delta x, delta y, okay? So I've got my setup. Initially, we're at the point 2, 2, so 2, 2. All right, and what we want to get to is in 3 steps. So we're going to go 1, 2, 3. We want to get to 1.4. Okay, now it didn't tell us the size, so we got to figure that out. So to get from 2 down to 1.4, I'm going to have to go down by 0.2. Down 0.2, down 0.2, down 0.2. So my delta x is a negative 0.2. And that's what we'll be doing each time, is just going down by 0.2. Okay, and again, that's arbitrary. We can make that whatever we want. This is what it is for this problem. Okay, what we need to do is figure out what direction are we jumping, and this is how far we're going to jump. This will tell us how much the y changed. So I use the differential equation, x times y. 2 times 2 is 4. And then to get the y, I'm moving in this direction this much. So 4 times negative 0.2 gives me a negative 0.8. That's how much my y changed. 2, take away that, will give me 1.2. All right, now to get to the next one, I have to multiply those. So now I need a calculator. Sometimes they make it so you don't need one. Sometimes they do make it so you do. This is 2.16. Multiply that by negative 0.2, and we'll get a negative 0.432. Okay, so now I'm going to take 1.2 minus 0.432, and it gives me 0.768. Okay? So almost there. We got to do this one more time. Multiply 1.6 times 0.768. I get 1.2288. Multiply that by negative 0.2. I get a negative 0.24576. So take 0.768 and minus 0.24576. Ended up with 0.52224. Now maybe you round that to 3 decimal points. Maybe you leave the whole thing. It's up to you. That's Euler's method, right? Take your point, put it into the differential equation, find your slope. Take the slope times your change in x to get the change in y. Do that to the y, and then you just keep repeating that however many times you have to do it. Right? Then they ask us to find a general solution to a differential equation. In order to do that, we have to separate this correctly. So I want that dy dx to separate. I want a side that has x times dx or something like that, and a y times dy or something like that. I need that to happen. So I'm going to add this over. So e to the y times dy over dx is equal to 6 cosine x. Okay? Then I'm going to multiply by dx. So I get e to the y dy equals 6 cosine x dx. Okay? And then what we're going to do is we're going to integrate both sides here. And so this is going to give me e to the y. Integral of e to the y is just e to the y. Integral of 6 cosine x is going to be 6 sine x. If I take the derivative, that gets me to here. And then plus c. And again, technically this would have a plus c, but since they're both constants, we don't need plus c. We can just have one side have it. It makes things a little bit easier. And so we always tend to make that on the x side. All right. All right, now the last thing we do, if we're trying to find a general solution, we need to get that y by itself. So we have to do the opposite of e to the y, which is natural log. So y is going to equal the natural log of 6 sine x plus c. And then that's our general solution. We don't have a specific point to put in, and so we don't have no way of knowing specifically what it should be. That's going to be our answer right there.